Thanks so much. It's especially fun for me to come in and talk about this because I have not talked about this with colleagues before. And this talk about life on small bodies has two little backstories that I want to share with you before I start. And the first one is that it really comes directly from the work that my fabulous friend and colleague Ben Weiss and I have been doing for almost 10 years now, thinking about how planetesimals in the early solar system heated up and what happened while they were heating. And then, which actually led directly to the Psyche mission too, ironically, because it wouldn't seem like they're immediately directly connected. And then the other thing about this is my co-author here, Stephen West. We are in the process of radicalizing undergraduate education through Interplanetary Initiative and the School of Earth and Space at Arizona State University. And for a number of years now, I've been teaching courses where what we do in the beginning is we set a big question, and it's the question for the entire semester. And the question that's the semester Stephen was with us, the question was, could life have arisen on small bodies? And what we do is the first day, give the students a little bit of a lecture. Now, these are undergraduates, graduates, all different areas of study. And so I gave them a little lecture, more or less on Ben's and my work on how planetesimals formed very rapidly in the first million and a half years of the solar system. And we know that this happened because we find meteorite fragments that tell us that they heated to the point that they differentiated into a metal core and a rocky exterior. They were hundreds or even 1,000 kilometers in radius, and they were the pieces that together accreted into our planets. And then we asked the students, knowing where we're trying to go, could life have arisen on small bodies? What is your natural next question? We call it a natural next question. What's the question not about the content we just discussed, but the one that will take us one step closer to our big goal? And then we vote on all the NNQs that the students write. We write them on the board. And whichever one is voted up to the highest level becomes the question for the next week. And 1 week, the question was, what is the evolution through space and time of an area within a planetesimal where there could be liquid water? And we discovered that that specific question had never been discussed in the literature. So we actually posed, the students posed, we didn't pose it, an actual well-posed research question that was unsolved. And so Stephen took it and we started working on it. And we haven't published this work, and it is a little bit preliminary, as you'll see, but I think really, really interesting. And then because he's actually a fantastic systems engineer, he ran off to work for Metis Technologies. He left with a master's in engineering from ASU and is now creating small sat missions to the moon. So that's the little backstory for why we came to this. And so the color here, I want to talk about the things that we think are needed for life to arise. And this is really a perfect talk to come right after Kat's talk because she, I think, convinced us all that everything can mix between everywhere and everywhere, apparently. And then the question is, are the things that are mixing actually useful? Could they contain life, and are they going to carry it across? And so the first thing we think about when we think about life is we think about the need for water. And of course, it probably didn't look like that sadly, on any early planets, because boy, I think we'd all live there. Maybe it looked more like some sort of rock and water combination if the heating was right. Or here's a picture I took in Siberia of a 250 million year old mud puddle. Maybe it kind of looked like that mud puddle on some of these early bodies. But we think that there was water, free water, on some of these early planetesimals. So water plus organic materials, some sort of organic molecules, and I thought that was the best picture of organic molecules that I found on the web. More about organic molecules later, but presumably we need organic molecules and water to make life. And then we need heat, some kind of energy. It can't be freezing. You've got to maintain your liquid water. You've got to have something that's going to trigger these organic molecules to keep doing whatever they do that the biologists can perhaps someday understand for us. But of course, on these early planetesimals, it's not the sun, it's probably radioactive heat from aluminum-26. And so that's sort of our scenario with these planetesimals. It's primitive chondritic material that contains ices and unmelted grains of metal and silicate minerals, plus aluminum-26. And then, of course, another thing we need is time. And that becomes the key question here, because I'm sure that we would get many opinions here about, given the right conditions, how long might it take for life to arise, but I'm going to bravely assert that we really have no idea. And so feel free to rebut me later at your leisure, but I would suggest we really don't know. And perhaps there's another thing. Perhaps there's water, organics, energy, time, and some other miracle that we don't yet understand. But this is where we're starting with this. Now, my co-convener, Penny, is a co-author on this fabulous Cruikshank et al. 2019, just freshly out, talking about these very same kind of conditions on Pluto. We've got the water, we have some heat, we have water ice, and we have water, and then we have got organic materials, and we have radiation, and so there are all these parts there. And so that's kind of where we're going with this small body conversation. This is so compelling to think about the life arising on Kuiper belt bodies, on comets, on the moons around the larger planets that we've got. All these things that Kat explained to us can be flung hither and yon and used for panspermia. But I'm going to really focus on planetesimals, those very, very first baby planets early in our solar system. And so the scenario is like this. In the protoplanetary disk, there was gas and there was dust. That's on your left, those little tiny things. And they accreted very rapidly into planetesimals. And planetesimals here are shown as consisting of fundamentally two different kinds of materials. The undifferentiated materials in some sort of spectrum of browns. So these are similar to chondritic meteorites. They have silicate and metal grains in them, and then presumably also originally they had either water or CO2 ices, other ices, and also perhaps hydrated minerals in them, but not melted. And then with sufficient aluminum-26, they would have melted completely and differentiated into an iron-nickel core, which is what we suppose that Psyche is, although we don't really know. Hopefully we'll find out in 2026 when we enter into orbit around Psyche. And then also igneous modified silicate minerals in the mantle. And then some of these things have been broken up through catastrophic impacts, and they exist in our solar system and in our meteorite collection today. And so that's how we put these things together. Now, a lot of these planetesimals presumably accreted into Earth and our other familiar planets, and some of them did not. Some of them were broken up into pieces or left in the asteroid belt, that kind of thing. And so an unsolved question, as if these aren't all unsolved questions, would be, if life had arisen on a planetesimal, is it possible that it could have persisted into the planet-forming stages? And I'll just say ahead of time that I don't see any reason why not, because not all planetesimals are going to be involved in the kinds of catastrophic collisions that would cause them to go into a plasma or otherwise completely denature anything that was created. Some things are going to fall, like Chelyabinsk, for example, back onto the surface of a temperate planet. So there is that possibility in the end. So here's the scenario we're looking at. Now I'm going to stick with the ones that did not fully melt. I would posit that if aluminum-26 heated these bodies up to 1500 Kelvin, that is not going to be good for the organic materials, the retention of the water, or the creation of life. And so one of the things that Ben and I have worked on a lot is how much can these things just heat up a little bit gently? How can they move a little bit beyond just the onion skin metasomatism of a chondritic parent body? Could they melt just a tiny bit? What would the internal process be like? And so planetesimals definitely had the right stuff. So here's the Murchison Meteorite. Here's a paper from 2019. Contains thousands of different molecular compositions, all organic molecules, that's what they're talking about, and likely millions of diverse structures. More than 35 amino acids have been found in Murchison. I wonder how many of you have ever been up close and personal with a piece of Murchison that had been carefully stored. Have any of you smelled it the way I've smelled it? And it smells like an oil well, basically, doesn't it? A sulfurous oil well. It's so filled with organics that that's what it smells of. And so as we've been thinking about this, and as Stephen was thinking about it, what could be a better place for the advent of life than a nice, warm, wet piece of Murchison? So that's the idea that we're starting with. And so here's the kind of planetesimal model that Ben and I have mainly worked on, something where it heated up so much on the inside that it actually did melt into a silicate magma ocean and a metallic iron core, iron nickel metal in the middle. But then on these planetesimals that formed early enough to differentiate, there's still additional material raining onto them from the protoplanetary disk. And so we posited that you would get a partially differentiated body in a lot of cases with unmelted, undifferentiated primitive crust. And if you imagine the heating process, this is internal heating. This is not the kind of heating we experience with volcanism on Earth. The interior is heating up and the surface is very, very cold. And so there's going to be a wave of heat that rapidly rises toward the surface and then gradually recedes again as the radiogenic heating calms down again. And so that will drive the release of fluids, including water, all kinds of messy, briny fluids, and they'll drive them near the surface. This is something Ed Young has worked on extensively. How much will be lost to space? How much will be frozen into the lid? How much will recirculate in hydrothermal systems? And then over time, as the body cools again, that wave of heat will go back toward the center, and eventually the liquids will freeze. And so a question is, how much of the time do you get just that right amount of heating? How long does the heating last? What is the region inside the body that is habitable? And I like this region inside the body idea very, very much. I wonder how many of you would agree with the notion that assuming that there is life scattered through our universe, the most common kind is going to be single-celled organisms living underneath the surface of planets. It seems like that's very often where the best conditions are that seem best to us from our Earth-based perspective. Also, absolutely the hardest to find. And so I would say we should take all of our extra money and give it to Honeybee and have them practice drilling more and more and just send drills everywhere. That's what I would like to do. All right, so that was the idea. Now here's some results that Stephen and I came up with. So in this case, we just looked at planetesimals on the vertical axis. This is the radius of the planetesimal from 1 to 25 kilometers. These are really small ones, because we think they went easily up to hundreds and then sort of Mars-sized embryos. But we're just going to look at things up to hundreds of kilometers in radius in this conversation. And then time of formation in million years after calcium aluminum inclusions. We all recall, of course, that calcium aluminum inclusions are those very first solids that condensed out of our hot gassy nebula filled mostly with refractory elements like calcium and aluminum. And so if we imagine that these planetesimals accreted perfectly and instantaneously at a certain time after calcium aluminum inclusions, simplicity of calculation is created that way, then we ended up with how much silicate melting would actually occur. And so the white part up here is, on the upper left, is bodies that would actually melt more than about 9% into the silicate melting field. And we decided not to think about those. We thought there would not be enough of the body that would be cool enough for organic molecules to really react. But even in the dark blue area down at the bottom where everything melted less than 1%, that's really great for melting water and creating nice, comforting, warm, wet places under the surface of these planetesimals. So lots and lots of bodies that fit the heating criteria. So this September 20th, 2016 was the historic day that we had that day in class where we thought of this question. And can I tell you, all you teachers, and some of you know, how fun it is to be in a class where the entire class, including the teachers, are all pursuing something that none of us understand. It's actually incredibly energizing and exciting, and all the students are 100% in, and on that day, when they asked that question, people were rushing up to the board and drawing pictures like, what could this mean? So this was our first picture. So again, Z, that's the depth into the planetesimal on the left-hand vertical axis, and then temperature. I can't remember exactly what H was. Who knows? Habitability? I don't know. On the horizontal axis. But what we're drawing with that curve is a schematic, a concept of where the liquid water comfortable, clement conditions for life might be inside this body over time. So in the beginning, very rapidly, first it heats up in the middle, and then it heats up toward the top, and so that habitable zone inside the body zooms upward in Z toward the surface, and then it persists along the surface in the lid of the planetesimal for a while, and then as the planetesimal cools, it begins to sink back down into the middle. And so we were wondering whether it could last as much as 100 million years. That was a number we were sort of playing with in the class as a time that would be required for life to form. And so that was our concept picture, historic concept picture for this crazy idea. So then Stephen takes it away, and so here's the maximum persistence of liquid water for planetesimals, again, just from 1 to 25 kilometers in radius, and from the time of formation, from time after calcium aluminum inclusions, from 0.1 up to 2.5 million years after calcium aluminum inclusions, and liquid water persists up to 14 or 15 million years in those small bodies. 14 or 15 million years, you know, what's your reaction? Whoa, way too short, life could never arise, or, you know, maybe it could. But these are for little tiny bodies, and so let's keep talking about what might happen in larger bodies too. And so this is my final slide, I think, and this comes from Ben's and my paper that we wrote with Maria Zuber when we were talking about the idea of a partially differentiated planetesimal. And considering bodies that are much larger, it turns out that even in our simple models where there's, and I'm just looking at heat flux, and it was a sort of a core to mantle heat flux question, because we were asking questions about magnetic field generation and so forth, that with instantaneous accretion or with some simple incremental accretion assumptions, we could keep these bodies warm in their interiors for tens of millions of years. And so this is meant to be just a kind of a thought problem for us all to consider. Could life actually have arisen on planetesimals? Could there be evidence for life in meteorites that we have not known to look for? And if this is so, how could they have been spread through the solar system? And many unanswerable implications of that possibility, including one that we talked about a couple of years ago, and then some people, I'm embarrassed to say I've forgotten their name. There was a brief paper out about could the moon have ever had habitable conditions? Well, it's exactly the same. Are they here? Am I insulting people who wrote this paper and I can't remember your name? Forgive me. But it's the same concept. You know, you have radiogenic heat, you have accretionary heat, you have bodies that definitely had fluids in them. For some period of time, there's some area under the surface of these bodies that are habitable. And is it enough time? I don't know. Maybe someone can answer. Thank you so much. Okay, fantastic. Time for one question, and apparently there'll be lots of time for questions later on the panel and so forth.
Thanks, great talk, Lindy.
Thanks.
Question, so a lot of origin of life theories involves, hypothesize the necessity of cyclic processes, you know, thermal convection in deep ocean vents or tide pools or hot springs or those things. Do you see, I mean, first of all, do you care? And secondly, is there any way to, are there any cyclic processes that you could imagine on these planetesimals, or might the whole thing be dead in the water because it's all too static?
Personally, maybe it's ignorance, but I don't know that cyclicity is absolutely required. I would, again, suggest that we don't know. But one of the nice things that Ed Young did in his quite comprehensive geophysical studies of planetesimals is showing that in a certain size range, you will get hydrothermal circulating in the lids of these bodies. And so that would be pretty analogous to what you're talking about. Yeah. Thank you so much. Sorry to go over.
Oh, that's great. We're good. We're good.